And welcome back to Calculus 2. In this video we're going to talk about alternating series, eventually leading to what is going to be our last convergence test. We've seen several of them at this point. I imagine you're wondering if it's ever going to end. Well, soon. Very soon. So, what is an alternating series? A series is an alternating series if each term flips signs, so it goes from negative to positive to negative to positive. All alternating series have a negative 1 raised to either an n or an n plus 1 or some offset of that. That's what flips the sign in every term. And more of these converge than just terms that are always positive or always negative, just because there's a canceling out effect with each one of these. So, since we're allowing for some negative terms, which we really haven't that much before, we might actually see more convergence than we did before. But here's the test we use for alternating series, specifically for them. And what it is you look at this series where you have your alternating series factor here, and then if you take that out, what function do you have left? Well, if you look at those u sub n's, the series will converge if those u sub n's are all positive, if they are eventually non-increasing, so they might increase for a finite number of terms, but after that they will always either decrease or stay constant, and they converge to 0. So not only are they decreasing, but they are decreasing towards 0. Infinitely close. If all of those are true, the alternating series will converge. So let's look at the proof of this. So note, for our given, we get to assume all three of these. So if we go, we know u sub n are positive, u sub n non-increasing, and u sub n converges towards 0. We need to show the sum k equal 1, or n equal 1 up to infinity of negative 1 to the n plus 1 u sub n converges. Technically, we'd need it to define for some capital N, but what that capital N is really doesn't matter, so we're just going to let capital N equal 1. And then look at the different possibilities. If little n is an even integer, so n equals 2m, where m is a natural number. Then the partial sum s sub n, or s sub 2m, equals, well, u1 minus u2 plus u3 minus u4 plus dot 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 plus u sub 2m minus 1 minus u sub 2m. Now note, since we started off with a positive term, when n equal 1, that'll be negative 1 squared, these are all positive numbers, because remember, u sub 1 is non-increasing, so this has to be either smaller in value or equal to u sub 1. has to be either smaller than or equal to u sub 1. So if I do their subtraction, I have to get a positive value. So s sub 2m is the sum of m, because I'm collecting them in twos, non-negative terms, so s sub 2m plus 2, the next even term, is greater than or equal to s sub 2m, because we just added another non-negative term, and the sequence is non-decreasing, if we reorder these terms, s sub 2m, and leave the first term alone, but then group everything else, so minus u2 minus u3, that's a non-negative term, minus u4 minus u5, plus dot dot dot, minus u2m minus 2, minus u2m minus 1, then minus u sub 2m. Notice we're just subtracting a bunch of positive numbers from u sub 1 to get s sub 2m. So that means s sub 2m is less than or equal to u1. So s sub 2m, the sequence, is non-decreasing, and bounded. So by the monotone convergence theorem, monotonic, monotonic sequence theorem, it must converge so s sub 2m, limit as n goes to infinity, of s sub 2m equals some limit L. So that takes care of the sequence of even partial sums. Well, what about the odd ones? Because we just looked at the even ones. I'm going to keep this in mind. Let's put a new page in. If n is odd. So n equals some 2m plus 1. Then s sub 2m plus 1 equals s sub 2m plus u sub 2m plus 1, just the next term. I mean, if you take the partial sum and just add the next term, that's the next partial sum. Since u sub n goes to 0, and we just saw s sub 2m goes to L, the limit as n goes to infinity of s sub 2m plus 1 equals, well, limit as n goes to infinity of s sub 2m plus u sub 2m plus 1. And we just noted this goes to L, this goes to 0, so the odd partial sum goes to L as well. Every partial sum converges to L, so series converges. It's a neat little proof taking the even partial sums out like that and working with it. But that's the test. Let's go back and look at it. This is the test. So what we're going to do now is we're going to do some exercises. Some of them may be using this test, some of them may not. So we're going to start off with this problem. This is problem 8 from section 10.6 actually in our textbook. And the tricky thing with the alternating series test is it has several conditions. Your u sub n's eventually have to be decreasing towards 0 is the big one. And they have to be positive. So you're ignoring this part. They're clearly positive. I mean, 10 to the n is always positive. N plus 1 to the factorial is always positive. But is it eventually decreasing? Well, probably the easiest way to get a sense of that, it's by no means perfect, but we can try it this way, is just to plot it. So if you do 10 to the n, and then divide by x plus 1, and we will call it factorial. We'll see if it can handle this. Math, no, it's probability actually. Let's look at the table. It's not showing up on the graph, but I think it will on the table. Alright, so 0, 1, 2, 3, 4. It looks like eventually it's non-increasing. The 10 to the n wins out initially, but then the factorial finally catches up with it. And we get tinier and tinier numbers. So yeah, it should satisfy the conditions eventually. I guess if you wanted to verify it, you'd actually have to do the limit problem, which we certainly could do. We've done that thing before. And when you're taking the limit of 10 to the n over n plus 1 factorial, n goes to infinity. We'd probably just do the trick we did before of n plus 1 times n minus 1 times dot 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 down to 3, 2, and 1. You have n tens on the top, so 10, 10, 10, 10, and 10. If you ignore the 10 over 10 factorial, then you're just left with 10 factorial, 10 to the 10th over 10 factorial. And then you've got the other part, the n plus 1, and then you got 10 over n. You got 10 over n minus 1, and then dot, dot, dot. Well, the thing is, since all of these have a larger number on the bottom than 10, all of these things are making it smaller. So this is less than 1 over n plus 1, and times 10 to the 10th over 10 to the factorial. But the thing is, this goes to 0, so this has to go to 0 as well by the sandwich theorem. So yeah, it fits the properties of the alternating series test. So then, it does converge, because this does go to 0. It does decrease. By alternating series test. It's often worthwhile to think about, would it converge if it wasn't alternating? And it's just a harder thing to do. I think I would probably do a ratio test on this to see if it would converge otherwise. If I did the ratio test, I'd have, I could ignore this. So 10 to the n plus 1 over n plus 2 factorial times the flip of that, n plus 1 factorial over 10 to the n. So that's going to cancel out the n, it's going to cancel out that, and leave me with n plus 2. So we'll have 10 over n plus 2. That goes to 0, which is less than 1. So this actually converges absolutely. As well. We'll focus on this a lot more in the next video. I'm not necessarily going to hit it that hard here, but a very common exercise we'll be doing is to determine whether a series is absolutely convergent or just what's called conditionally convergent. This is absolutely convergent, so it actually is both. Alright, let's look at this one. N over 10 to the n. First off, let's just see what that would go to. Limit as n goes to infinity of just that term, n over 10 to the n. I think would go to infinity. Yeah, because this would go to infinity and the exponent would go to infinity. So the question is then, will the alternating series change that? Well, I don't think the alternating series helps in this case because it doesn't go to 0. It might if we had, to the 1 over n or something like that, but yeah. This goes to infinity. Sequence diverges. Putting an alternating series on it isn't going to make it converge. The sequence diverges, so does series by nth term test. For divergence. Remember that test says if your sequence of terms doesn't converge to 0, the series cannot converge. It doesn't tell you anything about convergence, just says divergence happens certainly when the sequence does not go to 0. It might happen other times, but certainly if it goes to something other than 0, either infinity or nothing or a finite number, that's not 0. The series must diverge in that case. So this is exercise 13. We have the sum n equal 1 up to infinity of negative 1 to the n plus 1 square root of n plus 1 over n plus 1. Alright, first off, it is not absolutely convergent, because if we looked at just this and ignore the alternating series, this would basically be equivalent to a p-series. We could do this test, square root of n plus 1 over n plus 1. That's equivalent to square root of n over n. So you could just do a limit comparison test, divide by 1 over square root of n. That's going to multiply into the top. I'll get you n plus square root of n over n plus 1, which is just going to go to 1. So by the limit comparison test, these would have to have the same convergence or divergence, and 1 over square root of n is divergent. So would this be. But, because it's an alternating series, I think this will be convergent still. Because if you look at the limit, as n goes to infinity, of square root of n plus 1 over n plus 1, certainly these are all positive, that's trivial. But they do actually go to 0, because if you say divide top and bottom by n, the highest power on the denominator, limit n goes to infinity, you'll get 1 over square root n plus 1 over n. And then 1 plus 1 over n. This will go to 0 over 1, or 0, which is what we want, because remember, to apply the alternating series test, we need u sub n's to be non-negative, or actually positive. We need them to be non-increasing eventually. And that's fine. After 1, they're non-increasing. U sub n is greater than or equal to u sub n plus 1. And u sub n converges to 0. We just showed convergence to 0. This one's trivial. Certainly square root of n is smaller than n for any n larger than 1. So for 2, for 3, for 4, the bottom will be larger than the top. So this is true. It is getting smaller and smaller. If you're not certain, again, what you do is you graph it. Graphs are great for getting an idea of the behavior of a function. So if we plug in y equals the square root of n plus 1. I did forget to put parentheses around the top, so I gotta go back here and insert one. Divided by, in parentheses, x plus 1. And if you look at the graph, decreasing, decreasing. So, satisfies all the conditions of the alternating series test, converges by alternating series test. So it's a neat little test. You have to show a limit happens, but alternating series converge a lot more than just non-negative series because they don't have to go down quite as quickly. And here's a theorem you can use to estimate your error in approximating with a finite number of terms, with a partial sum, basically. If you have an alternating series that satisfies the conditions for the alternating series test, then whatever capital N you needed to satisfy the alternating series test, for n greater than or equal that capital N, the partial sum approaches the sum. Why is that? Well, it's because as you take your partial sum, with each subsequent sum, you're only adding one term. So s sub n is x sub n plus 1 is s sub n minus or plus the next one. So plus a sub n plus 1. And it's either positive or negative. If it's negative and it's converging, that means it has to jump around. Because if it's adding and subtracting, it's going like this. The sum is this nth partial sum. It hops above the sum, below the sum. So every term will just flip you one side of the actual limit, the actual sum of the series. So s sub n will approximate the sum of the series. So this would be an s sub n, this would be an s sub n, each peak would be an s sub n. And then the difference between the actual limit and the sequence would just be less than the next term. So you can actually just use that to estimate the error, figure out how many terms you need to get within any error you want, and then just go from there. Also, because successive sums are just going to jump above and below, the actual limit, the actual sum of the series, is going to always lie between two partial sums. Because one's going to be an underestimate, the next is going to be an overestimate. Underestimate, overestimate, underestimate, overestimate. That's the way it has to be with alternating series, because by nature you're adding and subtracting. If you're going to converge to something, that means you got to hop around it. Whereas if you're all positive, that means you're adding on every time. You have to be going up towards it but leveling off. If you're decreasing towards it, be like that if you're only negative. So yeah, sum lies between any two consecutive partial sum. Let's do an exercise. So this is problem 54 from the text. Determine how many terms should be used to estimate the sum of the entire series with an error of less than 0.001. Well, we just saw that the difference between the nth partial sum and the actual limit is less than, well, u sub n plus 1. U sub n plus 1 is just this formula with n plus 1 plugged in, so that would be equal n plus 1 over n plus 1 squared plus 1, and we want that to be bounded by 0.001, or 1 over 1,000. So doing some simplifying, that's n squared plus 2n plus 1 plus 1. So we got n plus 1 over n squared plus 2n plus 2 is less than 1 over 1,000. Cross multiply. Everything's positive, so I shouldn't have to flip the inequality. N plus 1 times 1,000 less than n squared plus 2n plus 2. That's 1,000n plus 1,000. Take that over to the other side. 0 less than n squared minus 998n minus 998. Can solve this quadratic inequality by doing quadratic formula. 998 plus or minus the square root of 998 squared minus 4 times 1 times negative 998. Plugging in the c. Although I guess both b and c are negative 998, so it doesn't really matter. Don't have to worry about the sign that much. This one's positive because it was squared. This one's positive because it's negative b. You plug that into your calculator. Can ignore the minus one, because that'll be a negative number. We don't want n to be negative. Plug it in. 998 plus the square root of 998 squared plus 4 times 998 divided by 2. Well, you get about 998. Just right about 999. So if n is greater than or equal to 999, our partial sum will be within 0.001. One thing you might try is just see if you can get that sum in your calculator. I think that is probably too many terms for this one to do. I mean, this doesn't have a very complicated processor in it, but let's see if it'll do it. That would be, I want to create a sum of the sequence. Oh, that's a props. Yeah. Let's see, the sequence would be n over n squared plus 1s. So x divided by x squared plus 1, comma, x, comma, 1, comma, 999. Close the sequence, close the sum. It's gonna chug for a while. Oh, it did. 6.8126. That's within a 1/1000th, so rounded off to 6.813, we know it's at least that accurate. So that's neat. Alright then. That's going to be the end of this section. Next time we will finish it. We will actually continue our talk about alternating series a little bit to talk about the rearrangement theorem, and then we'll move on to just some general convergence or divergence problems since we're getting to the end of our convergence tests. See you then. Have a great day.